So you've come to us with a fascinating challenge. You want the blueprint for designing the architecture that powers, well, so much of the modern web's real-time data flow. We're talking about that resilient high-throughput beast known as the distributed log. The kind of system you see with technologies like Kafka.
That's exactly right. And this isn't just about, moving data from point A to point B.
Oh.
It's about creating a foundational infrastructure that can handle these continuous, massive data streams. We're talking billions of events a day, while absolutely guaranteeing reliability and order.
Okay, let's unpack this then. We're diving deep into the engineering decisions that make real-time data streaming even possible.
Our goal for this deep dive is really to synthesize the source material and uncover not just the components, but the fundamental design principles and best practices. We want you to walk away understanding how these systems ensure scalability, fault tolerance, and data integrity, even when hardware inevitably fails.
Let's start with the core reason these systems even exist in the first place, which is decoupling. What's the fundamental job of a message queue in modern architecture?
At its heart, it's the ultimate buffer. The message queue's primary function is to break the direct dependency between the producers.
The services creating the data.
Right, the services creating and sending data, and the consumers, which are the services that are processing that data.
I think the logistical analogy here is just perfect because it makes that decoupling so tangible.
The factory and the store.
Exactly. Producers are like the factories, just constantly shipping goods, churning out data, and consumers are the stores, receiving those shipments ready to process them.
And if that store, the consumer, suddenly gets overwhelmed or, say, its loading dock breaks down, the factory doesn't just stop.
It keeps on producing.
It just sends the goods to a central warehouse. And that's our message queue. That warehouse, that intermediary, is what we call the broker.
The broker.
Right. Brokers are the central infrastructure. They're responsible for storing, managing, and, delivering all of those messages.
So the broker holds the inventory. But if you're dealing with a massive amount of different data user clicks, financial trades, sensor readings, you need some internal organization. And I guess that brings us to topics.
Yep, topics are the logical categories. They group related messages together. It's like classifying your inventory into specific product lines: electronics, produce, clothing.
So producers write to a topic, consumers subscribe to the topics they care about.
Exactly.
But if a single topic is getting, say, 1 billion events a day, how do we prevent that one topic from becoming a massive bottleneck?
That's where the really ingenious design choice of partitions comes in. Topics are deliberately divided into multiple partitions. The partition is the fundamental unit of concurrency and scalability.
So you're splitting it up.
Right. By splitting a single logical topic into multiple physical partitions, we enable the system to process all that data in parallel.
So if I set up a topic with, let's say, 10 partitions, I can now, theoretically, assign 10 different consumers to read that data at the same time, boosting my throughput tenfold. So the partition is really the key to horizontal scaling.
Exactly. But it's not just about speed. It's also about order. And this is a really critical difference between a distributed log and a traditional queue.
Okay.
The messages within any given partition have to maintain a strict sequential order.
And that order is guaranteed by something called the offset.
Precisely. Each message inside a partition gets a unique, sequential, and immutable ID, the offset. So if your partition receives messages 1, 2, 3, and 4, you are absolutely guaranteed that a consumer will always see them in that exact order. This immutability is the bedrock of the log architecture.
And this offset, this is where the fault tolerance starts for the consumer side, right?
Right.
Because the consumer is tracking its own progress.
Yes. A consumer never says, hey, I'm done with message 5. Instead, it says, I'm committing offset 5. It stores that offset, usually externally.
So if it crashes...
If the consumer suddenly crashes, if the store burns down, when it restarts, it just checks its last committed offset and resumes processing from, say, offset 6. It doesn't ask the broker where it left off. The consumer is responsible for its own state tracking.
That's a huge distinction. The consumer managing its own progress. It feels like a real shift from older messaging patterns. But wait, if the consumer is responsible for committing that offset, isn't there a critical risk?
Go on.
What if the consumer processes message 5, but then it crashes before it can successfully commit offset 5.
That's a fantastic and a really crucial question. It highlights the design trade-offs. If it crashes after processing but before committing, when it restarts, it's going to read offset 5 again.
So you get duplicates.
You can. This means the system provides what we call at least once delivery. The design prioritizes not losing data over potentially duplicating the processing. So for really sensitive operations like financial transactions, the consumer application itself has to be designed to be idempotent.
Meaning processing the same message twice won't change the final outcome.
Exactly.
Okay, so we have data order through offsets and parallel processing through partitions. This brings us perfectly into the next layer, reliability. Because we've established that physical brokers will fail, how do these systems guarantee durability when a piece of hardware just dies?
What's really fascinating here is how these systems guarantee resilience. The answer is replication. Data durability isn't achieved by just saving the log once. It's done by making sure that every single partition is replicated across a configurable number of separate brokers.
So that's our safety net. But okay, that introduces a new problem. If I have 3 copies of the data and the main broker goes down, how does the system decide instantly which of the other 2 replicas becomes the new source of truth? How is that continuous operation maintained?
That's where a core engineering process, leader election, takes center stage. For any given partition, one broker is designated the leader.
The leader.
All producers write to the leader, and all consumers, ideally, read from the leader. The other copies are called followers, and the followers are just constantly pulling data from the leader to make sure they're synchronized.
If the leader fails.
That's when the cluster initiates a leader election. The key requirement here is that the new leader must be one of the in-sync replicas, or ISRs.
So one of the followers is fully caught up.
The ones that are confirmed to have the absolute latest committed data. The system requires a quorum, usually the majority of replicas, to agree on the new leader. This guarantees that the system fails over immediately to a reliable, fully updated replica. And that seamless handoff is what ensures continuous operation.
Okay, so that's the durability aspect solved. Let's pivot to scaling, the other huge promise here. We said partitioning allows for parallel processing. How do these two concepts, replication and partitioning, work together to allow for massive horizontal scalability?
Well, they separate the concerns beautifully. Replication handles the durability and the fault tolerance.
The safety.
Right. Partitioning handles the throughput. The architecture lets you scale horizontally by just adding more brokers and, crucially, adding more partitions. If you need to double your system's capacity, you deploy more machines, create more partitions for your topics, and then assign more consumer processes.
So you're just spreading the work out wider, not trying to make a single computer faster.
Exactly. The practical result is that increased partitions allow for, exponentially more consumers to process data in parallel, which boosts the overall throughput significantly. This capability is why these systems can comfortably handle that billion event scale without a single point of failure.
Now that we have the architecture down, let's try to ground this in the real world. What does this actually look like when companies deploy this kind of tech? Where is this distributed log architecture hiding in our daily digital lives?
It's basically the central nervous system for modern enterprises. Our sources highlight 3 main high-stakes categories. First is processing high-volume, continuous streams, like all the website activity you generate.
Every click, scroll, and view.
Every single one. It all needs to be logged and processed immediately. That's a massive fire hose of user engagement data.
Okay, what's second?
Second, handling the highly sensitive high-stakes streams like financial transactions and stock trades where every millisecond matters and the order is absolutely non-negotiable.
And third?
And third, managing these voluminous streams of sensor data in real time, whether that's, fleet telemetry for delivery trucks or machine logs in a smart factory.
And these aren't just logging tools. They're actively shaping how companies build their entire backend.
Oh, absolutely. They are the backbone for several critical architectural patterns. We see them used to build massive data pipelines, moving data reliably between operational databases and analytical data warehouses. They also enable real-time analytics, letting companies make instantaneous business decisions based on fresh data.
And maybe most importantly, they facilitate the development of event-driven microservices architectures.
That's the ultimate payoff of all this decoupling we talked about. Instead of Service A directly calling Service B, Service A just writes an event to the log. Then Service B, C, and D can all react to that same event independently on their own time. This makes the whole system far more flexible, resilient, and easier to update.
Because every service is just reacting to a shared, immutable history of what happened.
Precisely.
That architecture is clearly powerful, but, I mean, achieving that kind of performance in a mission-critical environment isn't just about setting up the initial components. It has to shift into optimization and maintenance.
Yes, and if we connect this to the bigger picture, maintaining a healthy, efficient system requires constant attention to the details, the little things that ensure long-term stability and, cost efficiency.
So what are we monitoring most closely to ensure the system is healthy?
You need ruthless visibility into two things. First is message latency, how quickly data moves from the producer to the broker. If that spikes, you have producer issues.
And the second?
Second, and often more critical, is consumer lag. Lag tells you how far behind your consumers are getting in processing the log. If that lag suddenly grows, your real-time analytics are now delayed. You could be losing money or missing critical operational alerts. Monitoring lag is an absolute prerequisite for maintaining your service level agreements.
And since these logs often feed really complex systems and contain sensitive data, what advanced design choices do we need to make to ensure quality and security?
Okay, let's start with security. It has to be implemented through authentication to confirm identity, authorization to control who can read and write, and robust encryption to protect data, both in transit and at rest. Security can't be an afterthought. It has to be intrinsic.
Right. And what about data quality? When you have hundreds of services reading and writing, the definition of a user event or a transaction might change over time. That's schema drift, and it can crash consumers.
That is the classic poison pill problem. If a producer suddenly changes the data structure, the schema, an older consumer trying to read that new message will deserialize it incorrectly, crash, and then get stuck in a loop trying to process that same poison pill message. It's a cascading failure.
So how do you prevent that?
That is why schema registries are mission critical. They enforce data consistency and compatibility, making sure that any changes are backward or forward compatible before they ever even hit the log.
That's a huge layer of protection. Now let's talk efficiency and cost, especially for logs that might stretch back years and years.
For long-term efficiency, you can use techniques like compaction. Compaction is an optimization used specifically for topics where you only care about the latest value for a given key.
So it's essential for topics that hold state, not just events.
Precisely. Think of it like keeping only the most recent bank balance for a user, or their current location in a tracking system. It eliminates all the redundant history and drastically reduces storage costs while still keeping that log structure.
What about performance?
Well, for performance, especially with high-volume data, compression is mandatory. You compress data before it even hits the network and while it's stored, and that saves significant resources on network bandwidth and storage space.
And for data that gets old but can't be deleted for compliance reasons.
That's when you implement tiered storage. You move the older, infrequently accessed data off the expensive, high-performance brokers and onto cheaper, slower storage. It dramatically reduces your operational costs without you having to lose that data archive.
Finally, what about resilience in terms of just the overall design strategy? We can't just rely on default settings.
No, you can't. The primary strategic design decision is the careful construction of your topic and partition strategy. The number of partitions isn't arbitrary. It has to be explicitly optimized for your expected read and write throughput and how your data is keyed. Poor partitioning can lead to an uneven load, what we call hotspots, which completely defeats the purpose of horizontal scaling.
And that ultimate final layer of defense.
You have to regularly back up your data. You have to implement robust disaster recovery planning, while replication guards against hardware failure within a single region. A truly catastrophic failure requires external, consistent data backups to prevent complete data loss.
This has been a complete tour from the architecture of decoupling all the way to the advanced operational best practices that keep a system healthy. You now understand the producers, consumers, brokers, topics, partitions, offsets, replication.
And the necessity of leader election and schema consistency. These are the core concepts that really define modern real-time data flow. You now possess the conceptual tools to design and even critique these scalable, reliable, and fault-tolerant distributed log systems.
Let's leave you with one final thought, tying everything we just discussed about durability and real-time processing together. If the goal is truly instantaneous, fault-tolerant processing of global financial transactions, you have to rely on replication across continents. But because of the finite speed of light, that replication introduces unavoidable physical latency. So how does that inherent constant latency fundamentally challenge the design of perfect data consistency at a global scale? And how do designers choose between speed and absolute transactional certainty? That's the question that keeps the top system architects up at night.